Hi, this is Sarah Cortina, and I'm going to be showing you how to do workshop number 4, problem 2A, B, C, and D. So part A asks us to write the equation for the chemical reaction that's described, and it says that you start with ammonium ion. So we're going to start with NH4 plus aqueous, and then you have the nitrite ion, which is NO2 minus aqueous, and that reacts to form nitrogen gas and water. So nitrogen gas is N2 gaseous plus H2O liquid. So that's part A. For part B, we're asked to find the rate law and to support it with calculations. So you're given the rates and the molarity of experiments 1, 2, and 3. So we can see that in experiments 1 and 2, experiments 1 and 2, NO2 is held constant, so we're going to start with that. So if we hold NO2 constant, then the only thing changing is the ammonium ion. So that's what's changing in this experiment. So in order to find the rate law through calculations, we're going to set up a mini rate expression. And we're going to make sure to put the faster rate on top. So we're going to do rate 1 over rate 2. And we're going to set that equal to K, which is the equilibrium constant. I want to make sure we have that, times the NH4 plus concentration raised to the N power, because N is the order that we're trying to find, which gives us the rate law. And we're going to do the same thing on the bottom, raised to N, and we're going to put a subscript there and there just to make sure we have 1 and 2. So the rate for experiment 1 is 7.2 times 10 to the negative 6 moles per second, or molarity per second, and rate number 2 is 3.6 times 10 to the negative 6. And that is going to be equal to 0.24 molarity raised to the N power, or 0.12, so 0.12 molarity raised to the N power. And we crossed out the K's because they're the same in top and bottom. So we're going to bring these down. When you divide 7.2 divided by 3.6, you're going to get 2. And you also get 2 on this side, and it's still raised to the N power though. We can't cancel that out yet. So to bring N down, to get the exponent down from there, we want to take the log of that. So we're going to take the log of both sides, and that lets you bring down N. And when you do that, you can divide both sides by log of 2 to isolate N, and then you get that N is 1. So if N is 1, remember we have N up here, then the rate is NH4 plus to the first power. Okay, now we're going to do part C. So for part C, what's being held constant is the ammonium ion. So we're going to look at experiments 2 and 3. So if you hold the ammonium ion constant, the change is in the nitrite ion. So we're going to do the same thing. We're going to do a mini rate expression, and this time the faster rate is in experiment number 2. So again, we have rate 2 over rate 3 is equal to K NO2 minus raised to the power of N subscript 2 and K raised to the power of N subscript 3, just so we know. And so then when you plug in the numbers that you're given in the table, you have 5.4 times 10 negative 6 with our units, and 3.6 times 10 to the negative 6 with our units, which is equal to 0.15 with our units again, raised to the n, and 0.10 n raised to the n. So now again, we're going to divide, and you get 1.5 and 1.5, and this is still raised to the n power. So again, to bring the exponent down, we're going to take the log of both sides, so you can bring n down there. And then you can divide both sides by the log of 1.5, and you get n is equal to 1 again. So then you get that the rate of the nitrite ion is this. So you get 1 to the first power. So the rate law of our overall reaction, we get that rate is equal to K, our equilibrium constant, times the concentration of NH4 plus to the first power and NO2 minus to the first power. And we proved it with n equals 1 and n equals 1 here. So now part D is asking us what order kinetics this reaction would follow. So to find that, what you do is you have your rate order is equal to n plus m, with m being one of these numbers. So for us in this order, we have 1 plus 1, and that equals 2. So that tells us that we have second order kinetics happening in this reaction.